Okay, well, welcome back. And now we are going to continue on in the course with discussion of research methods. And we're going to focus primarily on research methods specific to human factors. But in order to do that, we also need to do a brief little review of research methods related to behavioral science and psychology research in general. Because there's a few basic lessons that, number one, I just want to make sure everyone is aware of and is on the same page here. I'm not going to assume that you've necessarily had the research methods course, though if you had, then this is likely to be somewhat of a basic review for you in some regard here. First thing, though, is let's talk about different categories of research methods. So at least, again, those that fall under the heading of human factors. So we might think of human factors, as I noted in the introductory lecture, about applied psychology. So we might think it's all about doing applied research. And that is definitely true, of course, that there are plenty of applied studies that are done by human factors researchers. But human factors researchers, including the group that we have here at UCF in our psychology, human factors and cognitive psychology program, also do a great deal of basic research as well. And basic research is defined here as research that's done for the purpose of simply just trying to learn something new about, in this case, human behavior. Applied research is about solving a very specific applied problem. So if I'm doing research and I want to understand something about the limits of human memory, and I want to understand the issues about how human memory functions and develop a theory or test a theory of human memory, that would be basic research, right? I'm studying it for the sake of understanding that particular topic. But if I want to do a study where I am comparing two different designs of a computer keyboard to see which one results in faster typing speeds and perhaps more accurate typing, then that would be an applied question, right? I'm solving a very specific problem. Which one of these keyboards are better? It doesn't necessarily solve any sort of core theoretical problems in science. But human factors professionals and researchers could likely do both, right? Because if we are concerned about human memory as something that might, especially our tendency to forget things and lose track of information, as something that might explain why people will occasionally make errors, well, doing some additional memory research might help to understand this. And so human factors researchers are motivated to do both the basic research into human limits and human capacity, as well as the applied research to solve specific problems. Some studies are done in the laboratory, especially a lot of basic research, but we also may need to do field studies, that is, studies of people doing things in the real world. And certainly that's an important part of applied science, is to understand human behavior in the real world as opposed to in the laboratory. We're also going to talk about correlations as opposed to true experiments. We're going to have to get into that in a couple of slides. We'll also look at modeling and simulation research and also how to study user experience and concepts related to usability. So as I've noted here, the distinction between basic and applied research is basic is research for the sake of solving a scientific problem and just answering a question because we're interested in knowing the answer to it. Most of experimental psychology falls in this regard. So we can oftentimes subdivide experimental psychology into all of the different kind of domains or specialties in psychology. So we can do cognitive psychology research, and this involves a lot of studies, as I just noted, in memory, but also reasoning and decision making, maybe attention research, and all of that sort of stuff falls under the heading of cognition. And so we're going to think that's cognitive research. But also, of course, there's sensory research. So if we want to understand the basics of how vision works, how depth perception works, how hearing works, how do we localize sounds in our environment, that's all kind of sensory and perceptual research. That is part of experimental psychology. Developmental research, and that's actually relevant to human factors, by the way. So developmental research, if you've taken the developmental psych class, you may have been exposed to the ideas of people like Piaget who describe how our reasoning abilities develop through various stages, right? Going from sensory motor stages to pre-operational thinking and concrete operational thinking and formal operational thinking. Those are the 4 stages in Piaget's theory of cognitive development. And that is potentially relevant because something that we need to think about in human factors applications is, as noted in the introductory lecture, we have to honor the user, right? And that means we have to know the user. And sometimes users are not all just adults, right? So people use technology at different stages across the lifespan. And the way children use technology is not the same as how adults or even older adults use, young adults versus older adults use technology. And so understanding differences across the lifespan in terms of cognitive ability, reasoning skills, memory skills, personality, perceptual abilities, motor abilities, these all change across the lifespan. And understanding the age of the user is important to understand the user directly. In fact, if you've ever noticed when you look at children's toys, there's oftentimes suggested ages on those on the labels, and that's because research has gone into understanding what kinds of physical and or cognitive skills are needed to be able to play with those toys. And they would understand that, well, maybe, you know, if the label says ages 5 and up, for example, then that might imply that children under the age of 5 would not simply have the cognitive abilities to be able to do whatever activities are involved with that game. So knowing who is the intended user and what their cognitive and motor and other kinds of abilities are would be very important for that, right? Personality research, I just mentioned, the idea there is that maybe people with different personality traits may have different tendencies to trust automation, as noted in the previous content that we've covered, right? How does personality predict and how do individual differences beyond what we just think of as their typical personality traits, right? So one of the more common and popular personality theories is called the 5-factor model, that says that everyone has these 5 core personality traits that we can use the OCEAN abbreviation for that: openness, conscientiousness, extroversion, agreeableness, and neuroticism. And we can debate the merits of that versus other personality theories like Hexico, but what we want to understand is if there are individual differences in things such as propensity to trust technology, to distrust or overtrust, what other individual differences besides personality might factor into that, right? And so looking at personality factors and traits and individual differences is an important part of human factors. Social psychology, we saw that with the technology acceptance model, right? That there can be some certain role of social influence in our use of technology and how we use technology. Neuroscience, certainly, of course, we want to understand the brain, and the brain and the nervous system plays an important role in all psychological processes. And abnormal psychology is another example where we want to understand pathology in psychology that might not necessarily be something that human factors professionals are keenly interested in, though I suppose that it can come up. For example, is it possible that anxiety relates to people's perception and trust of technology? And how does anxiety influence intention to use technology? These all are certainly important factors. And it might be the case also that people with social anxiety or social phobia disorder might certainly have some influences of how they interact with the technology and social environments, for example. Now, all of that's basic research. We just want to understand what these basic processes are, but applied research, as I noted, is solving a specific problem. So I have a list here of at least 4 kind of core psychology areas that are all examples of applied psychology. I'm sure that we can go further than this, but these might be our big 4. I could have probably thrown in forensic psychology and call that another big 5, but clinical psych is an example of applied psychology, right? We might do basic research in clinical psychology to understand the nature of disorder and psychopathology, but we also do applied research, which is to develop therapies like, say, cognitive behavioral therapy or other forms of therapy to determine how do we best apply what we know about human cognition and behavior to help people deal with their problems and treat these problems. And so that's the applied component, right? Is actually helping people, with their psychological problems. Previously, we've mentioned industrial and organizational psychology, and that is the study of how people work together as part of some sort of organization. And a lot of people who work in IO psychology work for, say, human resources or similar kinds of roles in companies to help determine, for example, how do we best incentivize people to increase their productivity, to increase their happiness and manage their stress and so forth in the workplace. How do we best design an organizational structure to ensure that communication within an organization works effectively? The study of teams, for example, can be a part of this. The study of how people work together in groups certainly can be part of IO psychology as well as human factors psychology and the study of team behavior. School psychology, applying what we know about human cognition and learning to help children learn in school, and maybe even to identify learning disorders and how to best understand and diagnose and treat those disorders. And then last, of course, the human factors psychology is what our theme is here. Let's now talk about research methods. So I want to start with the basics of doing what's considered a true experiment. So a true experiment is defined as having an independent variable and a dependent variable. And it usually would begin with a hypothesis that in an ideal world is framed as a cause and effect statement. And I would simplify that as basically something like, if X, then Y, right? So if X is true, then Y is true, or if X is true, then Y is false. It doesn't always have to be that kind of a direct, true kind of mapping. But the idea is that there is some direct causal relationship between the value of X and the value of Y. And we want to establish this causal relationship between these variables X and Y. So how do we do that? And the way that we do it is to do an experiment where we manipulate X and then observe corresponding changes to Y. And if we can isolate the relationship between the two variables X and Y, so that every time I manipulate some value of X, there is a consistent and corresponding systematic change in the value of Y. And I can also be assured that there's no other explanation for those changes in Y, right? Then I have isolated that relationship between these variables, and I have established the causality of the relationship between X causing Y. And that's the goal, in principle, of doing a true experiment. So what's one example of this in psychology? Well, let's talk about arousal and memory, for example. I have my coffee here today, so we might suspect that increasing arousal in the brain by through the use of a stimulant like caffeine and coffee improves memory functioning, right? So I'm phrasing that as a cause and effect. If caffeine levels increase, memory performance increases, right? So that's my if X, then Y kind of hypothetical statement. But in order to do this, I need to be able to manipulate caffeine dosage and then observe changes in memory performance as a direct result of that caffeine intake without any other possible variables that could explain variation. So I want to give my research participants various amounts of caffeine and observe their performance on memory tests. And if I can conclude that all of the variation on the memory test can only be attributed to variation in the amount of caffeine that I've administered to them and not to any other sorts of factors about those people, such as how much caffeine they may have had the earlier in the day before they signed up for my study, or how much sleep they got the night before, or what time of day I'm testing them, or what their background memory abilities are. Some people might just have varying amounts of memory skills, right? So if I can rule out all of those kinds of other extraneous variables that might influence why, but what I'm trying to do is really isolate the relationship between caffeine arousal and memory performance. Then if I've done this successfully in an experiment, I can conclude that X causes Y, right? And so usually it's good to have some sort of number of different groups that receive different levels of your manipulated variable. And that's what we call the independent variable. The simple version, it would be something like just having a single experimental group and a single control group, where one group, the experimental group, gets caffeine, the other group gets nothing whatsoever. And then we compare them on their memory scores. And if one group scores higher, we're going to attribute that to the memory, to the treatment, right, to the caffeine. But we might also get increasing levels of complexity by having not just two groups, but maybe 3, 4, 5 groups, right? If we want to manipulate a varying amount of dosages of the caffeine, and then of course study how much if we can see systematic changes in Y, then we can get a much more fine detailed picture of the relationship between the independent and dependent variables, and not just study the presence versus absence of those variables. Now, one thing that we are concerned about here, this is something that is true in all psychology research, but may especially be true when doing human factors related research, is known as ecological validity, or sometimes called external validity, which is we do these kinds of studies in the laboratory. And the reason we do it in the laboratory is that the laboratory gives us the ability to control the environment. Right, as I said, I want to isolate the relationship between my independent variable and my dependent variable in an experiment. And that means a laboratory gives me the ability to do this. I can control the whole setting of an experiment to ensure that there's no other possible variable that could influence subjects, right? If I'm studying memory performance in the real world, it might be the case that I give people a test of some items like a list of words or numbers to memorize. But if they're in a natural environment that might be noisy, for example, then the distraction of a noisy environment can influence their performance. And if some people are in a noisy environment and some people are in a medium noisy versus a high noisy or not noisy environment, then lots of differences there. So I'm losing control of the situation by going into the real world. So I want to put people into the laboratory so I can control the environment. But the concern is that the more that I control a situation and make that situation uniform for all of our participants in an experiment, the more in which that environment begins to not resemble reality, right? And one thing we also need to be concerned about is that oftentimes the way in which we try to measure and test the dependent variable is oftentimes fairly artificial, right? So I just said, as an example, I might give people a list of words or numbers to memorize as a way of testing their memory skill after I give them some amount of caffeine, right? But we might also think that is that an ecologically valid task? That is, how often when we are using memory in an everyday context, do I have to remember just a list of random words or numbers? It maybe comes up every now and then, but certainly that's not the normal everyday way that humans use their memory, right? To memorize random lists of items. So it might be that the ability to memorize lists of items in a laboratory study might not teach us very much about the more everyday use of memory that people just use their memory for in real life. So we have to be concerned about the artificiality of the laboratory setting, but we also have to be concerned about the constrained artificial nature of the tests that we use in the laboratory as well. How do we measure memory? How do we measure attention? And any other kind of cognitive ability in a laboratory measure? And what does that have to do with how people use those cognitive skills in the real world? That's also a question of the ecological validity of a measurement as well as the experiment itself. Another thing that we might be concerned about in a laboratory study is that when people come into the lab, especially frequently we use university undergraduates in laboratory research, right? So what's it like for an 18 or 19-year-old college freshman to come into a laboratory? This is a strange place, and you're trying to figure out, if you're that person, what's going on? What am I supposed to do? I know that they're monitoring me and measuring me and observing me do some kind of weird task, and I got to figure out why and what I'm supposed to do. And there's certainly something strange about that experience that might change a person's behavior a little bit and make them act in ways that's not entirely natural, very different than studying people in the real world. So it might be the case that a lot of times people's behavior in the laboratory is influenced by the intimidating nature of this situation, and their behavior is not necessarily entirely realistic. So let's go into the field, perhaps, right? So maybe when we want to study people in their natural environment so that we can look at more realistic behaviors. Here's just one simple example. Maybe I want to understand decision-making in pilots, right? So here the idea is that you have a pilot who in a particular situation, maybe a change in a weather forecast, wind speed and wind direction, and so forth, they might need to make changes to their heading, right? Maybe they need to climb or in altitude or change altitude in some respect or change their heading to go around a storm or something like that. And so these decisions, we want to understand, what are the factors that influence a pilot's decision making? Maybe I want to understand some things like what happens when pilots are fatigued because they're on a very long flight, 10-hour flight or something like that. And how does that influence their ability to respond in a decision-making task? And maybe I want to understand all these other factors, right? So doing it in a lab might be very difficult to do because what do I do? Do I have to put someone in a flight simulator? I could do that. Do I make them fly in a flight simulator for 10 hours to make them fatigued? Well, I could do that as well. Though technically it's perhaps an odd thing to do. And so I could try to mock up a laboratory setting here that would force the pilot to have to make decisions in a simulated flight scenario like this. And I could try to simulate the stresses of fatigue and so forth. But we might still be concerned that their decision-making abilities and behaviors in the laboratory will not still be the same because the pilot will always know that they are in a simulator, right? And that means that there's some certain stresses that simply cannot be simulated. And that would be the responsibility of having, maybe 200 passengers on board, and that everyone's lives are in your hands if you're the pilot. And that's something that we can't really truly simulate in a laboratory. So in that case, it might be that there might be something about wanting to study this in the real world when the pressure is really there that is much more valid for us to be studying, right? That we can never achieve the true kind of ecological validity that we really need in a laboratory study. So how do we do this in a field study instead? Well, what we would have to do is we would need to, obviously, I don't think it's quite appropriate that we manipulate situations in a real live airplane flying right somewhere, right? We don't want to do that. But what we can do is simply just start obtaining data, right? So all of the pilot conversations and so forth, that's all recorded in the cockpit voice recorder. And there's all kinds of data telemetry that comes from the plane so that we can understand what kinds of inputs the pilots have made and decisions that they have made. And maybe we can even put video into the cockpit as well and get all of that. So we can get a lot of data from pilots, and then we can look for situations where they had to make a decision and try to analyze and study those situations to see what influenced their decision making in that situation, and we can better understand pilot decision making in that regard. But there is a major problem now, right? Once we have made this choice to simply just observe and record pilot behaviors and decision making, we have switched from doing a true experiment where we have manipulated variables such as an independent variable, and now we have done simply just an observational experiment where we are just observing and measuring variables without manipulation. And so what we get, the data that we get, is essentially correlational in nature. We can study the fact that the presence of certain variables might lead to an increased likelihood of certain kinds of decision-making behaviors in pilots. And so we can study the relationship between those variables and establish that that relationship exists. But what we cannot do is prove that that relationship is causal in nature, that there's some sort of actual cause and effect relationship between the variables. And so we have the old proverb that you surely must know by now, that correlation does not imply causation, or I kind of like to say correlation doesn't prove causation, right? It could imply in the sense that the relationship might be causal, but it simply just doesn't prove causation. In order to prove causation, you have to have, that manipulation of the independent variable and controlling all these other factors that might influence the outcome. But there is that advantage, though, of course. So even though we have certain limitations that we cannot prove causation in correlational research, we can study things that we might not otherwise be able to study in the laboratory, right? We're going to get maybe more true to life behavior here. Here's simply another example of some correlational data, right? We were talking about developmental psychology before, so we have some data. This is fairly old data by now, but I think the numbers still look a little similar, maybe not quite exactly the same. A pretty big drop-off in internet use as a function of age. And so clearly there's a correlation between age and internet use. And this would be an example of a negative correlation in the sense that increasing age is associated with decreasing likelihood of internet usage. So these two scales here, the X and Y axis, are inversely, therefore negatively related to each other. Increase in one corresponds to a decrease in the other. So we might be tempted to ask, does that mean that being older causes you to be less interested or less likely to use the internet? Well, that could be a true statement, but certainly this data by itself doesn't prove that, right? It might be the case that there's other variables, right, that might influence a person's likelihood of using the internet, and that this relationship isn't all that important, right? So, and of course, if we really want to understand why, assuming maybe there is some meaningful explanation for the relationship between age and internet use, this data by itself doesn't necessarily tell us why, but what it could do is it could point us in the direction of doing further research on older versus younger adults, for example. So maybe what I want to do is I want to do something to look at, say, maybe it's sensory issues, right? We know that older adults simply have maybe a decline in vision, right? There's things that change with our eyes as we get older that makes people become farsighted. It's called presbyopia, and it makes it harder to focus on close-up objects, at least not without reading glasses. And in that situation, maybe reading small screens, cell phones, and so forth becomes more challenging for older adults, and therefore they don't want to tolerate having to deal with that, so they are just less likely to use this technology. Maybe it's a cognitive impairment. Maybe it's something about the kind of multitasking that's required sometimes when you're using internet-enabled devices that is too overwhelming. Maybe it's the fact that the technology changes somewhat frequently, and it's difficult to learn and keep up with and remember all of these changes. So maybe that's another issue, right? Or maybe it's something else altogether that's not really related to ability, but maybe it's simply just one related to income and access, right? And that older adults would be perfectly capable of using internet enabled devices, but for money and so forth. So in that situation, we would learn something about this relationship and maybe help explain the causal nature of this relationship, but only if we did further follow-up research to maybe study it in a laboratory, right? One way to do this, to turn this into a laboratory study, would be to recruit a sufficient number of younger and older adults and try to make sure that you have recruited maybe some older adults that have cognitive impairments versus those that do not, and see if you can't use that to determine their likelihood of successfully using technology, right? And maybe you could then start to point to certain cognitive declines as increasing predictors of likelihood to use or not use internet. Moving into modeling research here. So what do we mean by modeling, right? So model means to create a model of something, means to create like a mock-up or of something, right? But we can do this in a way with a computer model, right? And that means basically a mathematical model that helps us sort of simulate something that from the real world, right? So one example of this is something called ACT-R, right? That's short for Adaptive Control of Thought, R for revised. So there's a revised version from the original ACT model. And so the ACT model is it's essentially a computer program of sorts that works as a model of decision making. And it boils down to, if I just want to simplify it somewhat, as a series of if-then statements. So if I'm going to make I want to model human decision making and human reasoning, it might be the case that what we do is we go through a series of implicit if-then statements in our minds, right? And so I'm thinking, well, if this is true, then I'm going to do that. If something else is true, then I'm going to do something else, right? So that's really simple logic in computer programming, right? If, then, else statements in computer code are simple logical steps, right? So if some variable is true, do this, else do something else, right? And we can develop a fairly complex series of if-then type statements like that in computer code that might be able to make decisions for, and we can possibly use that as a way of modeling human decision making. So if I want to understand human decision making, I might try to design an ACT-R model that will perform this task for me so that I can then manipulate certain variables and see how the ACT-R responds to it. And then I might be able to predict human decision making in a given situation, right? One example of this is applying it to human-computer interaction, as I have here on the slide. So let's say, for example, you go to your bank's website, and your task is to navigate to some place in the website to do something like transfer money. So what you might do is, and this was especially true back in the 80s when this was first, or 90s perhaps more likely, but this was first designed in the 80s, but in the 90s we could apply it to the interaction with menus, right? So in the 90s, it was very common for most computer interfaces to have menu bars, right? So you navigate to the top of the screen and there's a menu and you click on it and it opens up a list of choices of options to engage. And you go through a series of steps where you click this option and then you click this option and then you click this option. And so each one of these steps is essentially if you're trying to do something, you're going to do this, and then you're going to do this and this and this, and it's called a decision tree. And by following that all the way through, you're going to be able to get to whatever part of the website you're trying to get to, or achieve whatever goal you're trying to achieve when using this computer program. And so in that situation, the way in which a user would navigate the site could perhaps be modeled by an ACT-R decision tree. And if we can use that instead of a person, that is, we don't have to run 100 people to interact with the website. We can simply just have the ACT-R model human decision making, and then we can study how do we improve it, how do we change that. More recently would be AI, right? So all of the chat GPT type AIs that we can use now are examples of modeling systems as well. In this case, they are language models called large language models, or LLMs. And so these are, again, a model of human language. It doesn't mean, and this is very important, of course, when understanding these kinds of systems, is that they don't really have minds, right? We have a tendency to want to interact with these things and actually assume that this thing knows what it's doing, but it doesn't really know anything, right? ChatGPT doesn't know anything. It simply is just responding to us in a way that seems to be statistically appropriate based on the data that it has been trained on, right? So it basically has been learning language by being exposed to a massive amount of language from the internet. It then detects statistical patterns and trends in human language, and then it simply just repeats those patterns. And it can generate novel statements, but all of that novelty is generated not based on some knowledge that the AI has, but simply just based on its a tendency to statistically be able to predict what it ought to say, right? So in this case, what's happening is that you ask the AI something, and the AI just says, well, most statistical likely answer to this text prompt that the user has given me is this. And it feels like, of course, a natural conversation in many cases when you interact with AI, but it is, of course, still based on pure statistical modeling of language. But if we want to understand human language, maybe we can study these kinds of systems. Maybe we can try to draw an analogy and think that maybe somehow the deep learning algorithms that LLMs use might be very similar to the brain mechanisms involved in human language acquisition. And so when children are learning language, maybe it's something very similar. I don't think that psycholinguists agree with that, but that's certainly a relevant speculation. Another example of a model is something known as Fitts law, which we'll come back to in later chapters when we talk about motor control, but this is a model of the human speed accuracy trade-off, right? We have this fairly common sense intuitive idea that when I try to do a task as fast as I can, I'm less likely of being able to be accurate when I do that task, right? So there's this sort of inverse relationship between speed and accuracy. The faster I go, the less accurate I am, and the slower I go, the more accurate I can be. And so we can have an actual mathematical model of the relationship between speed and accuracy and use that to predict when people might be likely to make mistakes. So using these models can help predict human behavior in situations where we don't actually have to test real life human beings, right? Because the model effectively captures typical human behaviors. Research on AIs as kind of research subjects is only now an emerging field. So we're not going to have many examples of this, but let me give you just one example of how we might be able to use an AI as a subject in a research study. And I'm going to have to go back to talking about developmental psychology again. I mentioned Piaget a little earlier. One thing that we like to study in childhood psychology is called the emergence of theory of mind. And this is when children, usually around the age of 4 years old, begin to understand the difference between what they know in their own minds versus what other people know, right? And this means that kind of a distinction between the self and other. It also entails the idea that it means that there can be things that I know that other people don't know, right? And that there's a boundary there between my knowledge and other people's knowledge. And the idea is that young children don't really understand this. So until they develop their own sort of intuitive theory of the nature of minds in themselves and in other people, that they might sometimes make mistakes. And the classic example of this, of a test of this ability, is known as the Sally-Ann test. And so usually it's a story in which you have these two characters, these two children, Sally and Ann, who are playing with a toy. And Sally takes the toy and she hides it in a basket. And then she leaves the room and she goes outside of the room where she can't see or hear anything happening in the room. And while Sally is gone, Ann takes the toy out of the basket and puts it in a box. And so now the toy's in the box. So when Sally comes back, where will she look for her toy? Well, from an adult perspective, we know that she's going to look in the basket because that's where she left it and that's where she expects it to be. And she doesn't know that Ann moved it while she was gone. But if we ask this of a young child under the age of 4, they will typically get this wrong and say that she will look in the box because that's where the toy is, and the child knows that the toy has been moved, and they fail to kind of realize that Sally will not share in this knowledge. So they don't yet have a good theory of mind. They don't have a good understanding of the boundary between what the child knows, who has been told this story, versus what Sally knows, who was not present when the toy was moved. If you can ask these questions to ChatGPT and other AIs, and Well, I wonder. There's already some data on this, right? But maybe I'll just save that for you to test out if you want to, right? What would happen if you were to ask these kinds of questions uh, to a large language model? Do you think it would get it right and understand that Sally will not know where the toy is? Or will it act more like maybe a human 3-year-old child and sort of naively say that she will look for the toy in where it's been moved, right? Um, and what does that mean if it does get this right? Right? Does it mean that theory of mind has somehow emerged in LLMs? Perhaps not, but you might want to think a little bit about what that could mean about human behavior if LLMs get these kinds of questions right or wrong. Related to modeling is simulation, right? So we're going to simulate. We might think that, ACT-R is a simulation of decision making, or that LLMs are a simulation of language, and that might be true. But when we use the word simulation, we might also be talking about some sort of a mock-up in the laboratory. I had mentioned with our pilot example earlier that what we would do is we would have our pilots in a flight simulator, right? And so now we have an actual simulation of a cockpit and flight environment in the laboratory. And that is a way of trying to make the laboratory a little bit more like the real world, because we have a simulated reality. Flight simulators, driving simulators, these are all examples of the use of simulation in the laboratory to try to test more realistic and real life types of behaviors, rather than just giving people artificial tests to memorize lists of words, as I mentioned before too, right? But even though we have certainly improved our ability to make very, very good simulations, we are still not completely accurate at perfectly replicating reality. And we may never be perfectly accurate at replicating reality, right? So we still have to worry about this issue known as simulator fidelity, right? How close is the match between the simulated reality and actual reality? And certainly the closer we get, perhaps the better off we are at doing simulation research. And there are certain advantages, of course, right? So if I want to, like I said, test people in a flight simulation, that's certainly I can control and manipulate the situation if I want to, and I can just program that into the simulation to manipulate certain flight variables and weather variables that I would not be able to do if I wanted to do field testing of pilot studies. And then, of course, likewise, if I want to do things like maybe I want to test people's ability to learn how to perform a task like a maintenance task on a part. I could have that done in a virtual environment with a simulation instead of doing it on the real part, and that maybe is cheaper because it's easier to access a simulated version of a technology. I think I mentioned in a previous lecture the idea of training people on a task like an astronaut doing an EVA to perform repairs on the ISS, right? We want to do that in a simulation on Earth, which is much cheaper and easier to do than actually sending an astronaut up to the International Space Station and have them do it live for the first time in space. I have several pictures in here just to illustrate different types of driving simulators, and you can kind of get a sense of the varying amounts of fidelity here. So here on the one case is we have like this kind of 3-screen arrangement here that kind of gives us a slight sense of a panoramic view as a person sits in the driver's seat there. And we have, of course, a fairly realistic dashboard display and set of controls. On the bottom right is a slightly more advanced version where now we have an actual segment of a car that has seats and a real dash and even car doors and everything. And it's now surrounded by a much bigger, more immersive, large screen environment. But one thing to note in each case, though, is that even though we have an improvement in the in-car feeling of being in a car there, our display in this case is still pretty much a very obvious low to medium resolution computer animation, right? It's not reality, right? Same is true here. So here is something that might be something of the kind of the driver's side view, but here we're seeing that this is a slightly more interesting simulation because here we have a full car in this large dome. And so now the idea is that when you make a turn in a car, there are certain things that don't happen in a simulator, such as the feeling that you get as the car starts to turn, right? And in the real world, you can feel that. So obviously in this particular simulator, those kinds of rotational forces can be applied to the simulator, and you have this kind of full 360 all the way around view of the simulated environment. So that all will perhaps again increase our level of fidelity here. There's other concepts, by the way, when we talk about improving the fidelity of a simulation. We might want to create a sense of what's called immersion, right? So immersion is the sense of that you're getting immersed into a new reality besides the one that you're in. You sort of forget that you are in a simulator because you're totally immersed in this new surrounding. Everywhere you look, you see the virtual environment and not the warehouse or laboratory room that you were previously in. And that sense that you feel transported to a new place is known in VR research as a feeling of presence, right? So we want to understand what leads a person who's placed in a virtual environment or a simulator like this to feel present in the virtual environment. So you forget that you're in a lab somewhere, and now you think that you're really there in that virtual environment, right? You get very engaged with that virtual environment. And the idea is that we want to understand the factors that increase presence, because that we might think that by increasing that sense of presence, we're increasing the fidelity of the experience when a person is in the virtual environment or simulation. And that by doing so, we can then get more natural human behavior as opposed to that artificial laboratory behavior that we worried about before. So by increasing presence, we might be able to increase our ecological validity. Here's just another example here with flight simulators, right? Very clear fidelity differences between these two simulators, both in terms of the external environment, but also in terms of the cockpit display and layout. Very common for flight simulators to be mounted on these hydraulic systems so that the whole thing can move around, because certainly, especially with flight, even more so than driving, there are a variety of external forces acting on you, right? When you're climbing in an airplane, you're going to feel the change in your posture relative to gravity, and you're going to take on those G forces. Now, we can't necessarily cause an increase in G forces in these kinds of stationary flight simulators, but we can tilt them at least so you can feel that you're leaning backwards a little bit, right? And if the aircraft changes its pitch or roll or yaw, then the simulator moves that accordingly, and you can feel all of that inside of it. We're just not necessarily increasing or decreasing G necessarily. There are ways to simulate that in centrifugal spinning devices there that will test your ability to take G forces, but it's not very useful for a simulation like this. Here is this one is a helicopter simulator. So again, you can see it's mounted on the hydraulic system that can change the pitch, roll, and yaw of your aircraft here. Now, outside of driving and flight simulators, we can just have reality simulation, and that's virtual reality, right? So we use in VR typically a head-mounted display, right? And so the head-mounted displays will present a nice stereoscopic three-dimensional view of a reality. And every time you turn your head, the display turns with your head. It's very different than looking at a monitor, because when you're looking at a monitor, even a large monitor, your head movements are not linked to what's happening on the screen, right? But in VR, that's crucial, is we want to link, because that's the way reality works, right? In reality, when you turn your head, you see different parts of reality. And when looking at a computer screen, when you turn your head, you look away from the screen. But in VR, with the head-mounted display on, the screens stay in front of your eyes, and the display constantly updates every time you turn your head, so that you have a new perspective on the world that aligns with your change in head position and eye position. So that helps you, of course, feel that you're actually exploring a real three-dimensional environment. And you can even have, as you see, our user in the top left is wearing some gloves that also would track the hand and finger movements so that we can render in their field of view a virtual hand that they can see and use as a way of controlling and manipulating things in the virtual environment. This user also performs various gestures. I believe this gesture that she's performing here would activate some function in VR. Of course, we can do virtual training, like combat training is what's suggested down here, right? So there's even this kind of technology to have a virtual gun, although maybe that would also be a game too. And so here I just have a list of different kinds of VR technologies. The very typical example is called the head-mounted display, or HMD. And so now we've got to the point where having commercial VR HMDs like the Oculus Rift and HTC Vive is starting to become a fairly common commercial and home technology, whereas before these kinds of things were limited to the laboratory. And so there's some trade-offs here and some advantages and disadvantages of these kinds of technologies. So, the advantage is that you can have that movement linkage, right, that I described earlier. But part of the concern is that head-mounted displays restrict your field of view a little bit, right? It's almost like you have like something like this, or you can't see the visual periphery very well. And that's not, of course, completely natural compared to real life vision. So it's a little bit like looking in a tube a little bit, right? And so this is known to impact depth perception, for example. So there might be some concerns that there's still some distortion of visual perception that occurs in VR. And of course, we have to worry about the display resolution. Do we have true photorealistic virtual environments here? Perhaps not quite. Another example of VR, well, technically we might want to call it AR, augmented reality. And these are called head-up displays, or AR displays. This is commonly done in some cars, right, where you can have, in addition to information displayed on your dashboard display, you can have information that's projected digitally onto your windshield or windscreen. And oftentimes your speedometer can be up there and other information can be displayed. So that means you can keep your head up. You don't have to look down at your dashboard. The goal here is to allow the driver to keep their eyes on the roadway and not have to look away from the roadway to obtain some important information they might want. So you can keep that information up in front of them. Of course, there is the trade-off here of having that information kind of blocking your view of the outside world. Other examples of using this kind of augmented reality display would be technology like the Microsoft HoloLens, which is a pair of goggles that can be used to display digital objects on the screens of the goggles, but you still see through them to see actual reality as well. So you can have, this is why it's called augmented reality, is you can see both virtual and real objects all at the same time. Other examples of creating displays in VR involve the use of stereo goggles and projection screens. So let's take a look at that for a second here. So let's look at the cave. The cave is an environment here where you can see this person is standing in what looks like a little room, right? A little boxy room here with a cartoonish virtual world all around on the three walls at least, and the floor. There's actually no ceiling and there's no fourth wall behind our user here. And the way that this creates a sense of actually being in a real place and having a sense of depth and not just feeling like you're standing in a box is that this person is wearing stereoscopic goggles. And you can get a better sense of that in the picture perhaps on the right, where two researchers at the National Institute for Aviation Research are standing in front of a large rear projection screen. And that's what's also happening in the cave, is that the screen is rear projected. So there are projectors behind the walls here that project images up to that screen. And what's happening here is that in order to get good stereoscopic depth, what stereoscopic depth means is that the left and right eyes, usually we need two functioning eyes to have this kind of depth perception, have a slightly different view on the world because they're about 2 inches apart from each other, right? And this means that in order to have that kind of depth perception, we have to take into account the fact that the left eye view and the right eye view are a little bit different from each other. And one way to do that using stereo goggles like this is that when you display an image on the screen. You're going to display an image that's appropriate for the user's left eye. And then you're very quickly going to redraw the screen, but you're going to redraw it with an image that's shifted laterally a little bit, which would be appropriate for a user's right eye. And so the idea, like if you test this yourself, just by opening and closing your left eyes, you can kind of see how your two eyes see the world a little bit differently, right? Because everything might shift back and forth as you alternate with your left and right eyes, if you can see what I'm doing here with my blinking. And that's what's happening with stereo goggles, is that what's happening is that these stereo goggles can very, very quickly go opaque, right? So what happens is that maybe the right side goes opaque and the left eye can see, and that happens to coincide with when the screen is showing the left eye's view, and then it switches so that now the left eye goggle goes opaque and the right eye can see the screen, but now the screen has updated to show an image that's appropriate for the right eye's view on the world. And this is all happening, even though it means that the left and right eye goggles are shuttering off and on in an alternating fashion, and that the image being displayed on the screen is actually alternating between the left eye and right eye view in alternating fashion like that. It's all happening at 60 frames per second. And that means it's happening so quickly that you don't really notice it, and it just appears to be smooth, continuous, three-dimensional movement. And so you can get a nice, and 3D movies work a little bit similar, except now we use the colored lenses on the goggles to present the two images simultaneously on the movie theater screen. But because they are filmed through the different filters, that means the two eyes can see them through the different colored lenses on the goggles. There's a similar cave-like room here in our psych department at UCF. The lab is called UCF Immerse. And as you can see, this one also uses a rear projection, at least on the walls, but not on the floor like that. So that's just some regular carpet there. But the person, again, can use the stereo goggles to have a nice, compelling sense of being in a three-dimensional space here. Now, all of the technology that I've so far defined for VR simulation is essentially visual, though we can, of course, have auditory simulation as well. You can add headphones and create nice spatial experiences of sound. But something that's crucially missing in a lot of virtual experiences is contact, physical contact with a virtual object, right? If you have a virtual hand and you reach out and grab a virtual object, you might see the visual consequences of touching that object, but you don't feel the object, right? So can we have virtual touch or virtual haptics? And well, that doesn't work quite as well. We have some technology that's been around for a while and it hasn't quite been perfected. But what you're seeing here on the top is sort of an exoskeleton type device here. So that what happens is that if the user were to touch and grab onto, let's say, a virtual object like a ball, then the wires on the exoskeleton would tense up and prevent the user from squeezing their fingers any further than they currently are. And that would result in the equivalent of haptic feedback to say that, okay, I must have fully grasped this virtual object because I can't squeeze my hand any further than, at this point. But that's a strange kind of haptic experience because it's not like when you are grabbing something like my coffee cup here. Certainly, of course, when I grab my coffee cup, the solidity of the cup prevents me from squeezing any further than I am, right? But I feel that not as a constraint that prevents my fingers from moving further, but I feel that as actual solid contact on the palm surface of my hand. And this kind of virtual haptic experience does not create that sense of actual touch on the palm surface of your hand. It just kind of constrains how far you can bend your fingers until you meet resistance. The variant down at the bottom here includes adding on to that same exoskeleton now a multi-degree of freedom manipulandum that can constrain your whole arm movements as well, so it can provide resistance. So if our user grabs a virtual steering wheel, then obviously the framework around the fingers will prevent them from squeezing any further than the tops of the steering wheel. But then the manipulandum forces those hands to move in this kind of circular trajectory while they're grabbed onto the steering wheel. They can only make these circular movements here, rotational movements, right? And when they let go, then they would be free to make other arm movements, right? So this whole system works in a way that's maybe not so perfect, but at least that would be an attempt at trying to recreate the kinds of haptic experiences that occur in real reality. Next up, let's talk about usability research. So, and this is an important part of usability of human factors, right? To understand how people perceive a system in terms of can I use it? That's what the word boils down to. How usable is it? Can I use this technology? And so some important parts of usability would be how easy is it for me to learn how to use this technology, right? And how easy is it to use it once I've learned how to use it? And then if I stop using it and then come back and use it again later, how easy is it for me to remember all of these things that I've learned before? Sometimes when we come back to a technology we haven't used for a while, we might forget some things. So how memorable are is the system here? And so, well, here's some different ways that we can try to do usability testing and usability analysis here. So one way to do it is called front-end analysis. And this means that if I'm designing a new technology that I intend for people to use, then before I ever design it, and that is on the front end of my design, what I'm going to do is I'm going to start by thinking about the user. This is part of user-centered design, clearly then, right? And so I want to understand, who are my users? Am I designing for children, like toys? Am I a toy manufacturer? Am I designing for young adults, older adults? Or do I want to design for the whole population that might range from children through adults? And so I need to understand then who the users are and what their basic capabilities are and what their needs are, right? Why would a person use this device that I am making, right? So if I could be making, say, headphones. I just grabbed this as a prop since it's sitting next to me, right? This is a headset with a little microphone on it. So maybe I want to design this for people who are gamers. So I might predict that there's a certain age range that's going to use this. I need to think about the size of the ear cups as they go on a person's head. The size of a person's head, of course, is relevant here as well. And there might be differences in that between childhood and adulthood, and so on and so forth. So I need to think about all of the various conditions of use, and what kinds of features that this has. So maybe I want to interview users first. So if I ask users, if you were to have a technology like this, what do you want it to do, right? What kind of functions should it have? And so having all of that input from potential users of my technology before I start designing it is called front-end analysis. And that would be obviously very important to know, what are the expectations of the users and what are the capacities of the users, as I keep that in mind as I go through the design process. Now, after I have a functioning design, what I want to do is I want to do task analysis, and this is very important. So task analysis, we talked about in the introductory lecture with the bricklayers, right? The idea is that we need to break down a complex task into very granular levels. So building a brick wall is a task, right? But to analyze it at the granular level, that means bending over, grasping a brick with the left hand, grasping your trowel in your right hand and scooping mortar, and then applying the mortar to the brick and placing the brick and smoothing it out and so forth, right? And at each step along the way, there is something that has to be done, and there's some information that has to be acquired to perform each next step of the task. And so we can do the same. I think I did a task analysis in one of the earlier recordings about speed maintenance, right? That you have to look at the speed limit sign, remember the speed limit. You have to then look at your dashboard display and accurately perceive the indicated speed of the car. You then need to compare the indicated speed of the car as you perceive it to your memory of the speed limit, evaluate whether you are going too slow, too fast, or just right, and then decide on the correct response, right? So that means you have to decide to increase or decrease your speed or to do nothing. And that means you have to then also perform the response. So if you have chosen to increase your speed, then you have to press a little bit further down on the gas pedal, and exactly how much, and then when do you stop, right? So all of these are the small steps along the way to achieving the larger task goal, which is to get my speed to where I want it to be. But each step along the way has possibility of an error occurring here, right? So I say this micro level or grade level, highly granular level of analysis here is to break up these complex activities into these tiny little steps to understand what the user has to do and what the user has to know every step along the way. And again, when thinking about error analysis in the previous notes on error probabilities, we want to understand how something could go wrong at each one of those steps. And that's the importance of doing a task analysis, is we want to know where could the errors occur. Link analysis is something that it occurs when when a task has many maybe interacting moving parts. For example, like maybe for example, people are working together as a team. And so one person has to do part of a job, and then once that's done, another person's turn is to do something else instead, right? And so these things have to work together in appropriate sequences. And so how does it that the person number two knows when it's their turn? What kind of information do they get to know that person number one's job is complete, and now I can insert myself to do job number two? And so that's the link analysis, right? These are important links in the chain that determine that some complex process that involves multiple independent components all works together at the appropriate level. Another part of heuristic analysis, of usability testing, sorry, is called heuristic testing or heuristic analysis, right? And so the idea of a heuristic test is we're just going to have a human factors professional who has a good sense of what is good design and what is not good design, simply just informally test their a product, right? So the idea here is that, let's say, for example, some new computer hardware manufacturer has invented a new mouse, and they want somebody to do a heuristic test on it. So what you would do is just find somebody who's an expert in human factors and just have them use the mouse and say, yeah, this seems to hold up to my general understanding of human factors principles, and so it seems okay, right? Although it can be a little more concrete, and this is where Nielsen comes in. So Nielsen has developed 10 very specific usability heuristics, that is, things to consider when thinking about whether a system is meeting certain expectations, certain usability expectations. So you evaluate all 10 of these things in a heuristic analysis, and then you might be in good shape. So is the system visible or transparent? And that means it keeps the user informed about what it's doing. So we've talked before about keeping the human in the loop, right? And so that's relevant as well. So does the system keep the human in the loop, or is it more closed off and keeps everything that it does secret and people don't know what the system is doing, right? That would be a violation of that heuristic. The control mapping here. So if I do something with the device, right? Like, for example, with a mouse, I expect that if I grab a mouse and move it, that my cursor on screen is going to do something, right? And there's a mapping between the motion of my hand and the motion of the cursor on the screen. And that should match my expectation, right? And if somebody has designed a mouse that does something else that's very different, then that mapping might not map my conventions or expectations, right? I put WYSIWYG in there because that's a what you see is what you get. And that's kind of relevant here, I think. So, I mean, that comes up in things like a font menu, for example. So if you're in a word processor and you want to select a font, it's nice for that font menu to actually display the font name in the font style that it is, so that you know what you're selecting. And that's something related, I think, to having a mapping there between what the user expects and then what they get. Autonomy here. Is the user allowed to have some control over their actions? And that's an important thing, is that people like to choose when to use technology and how to use technology. Consistency. So sometimes the idea is that you can have a system that its controls work one way in one context, but when you change some mode or setting on the device, then suddenly the controls do completely different things. This was a problem actually a few decades ago when home stereos and home video equipment like VCRs and DVDs and so forth. There was a phase where when they were originally designed, they had just lots and lots of buttons all over the place. And then people decided they didn't like these messy looking devices with dozens of buttons on them. So everything went minimalist, and you would only have like a few buttons, and you would have to be able to change modes. And that, depending on what mode you're in, those buttons do different things, depending on whether you're switching mode to, say, control on a stereo receiver, for example. You could switch between controlling the CD player versus controlling the tape deck. And you might have to just change one mode to switch between those different functions. And depending on which mode you're in, one of these buttons would perform an action like start or stop the CD, but change modes, and now maybe that button ejects the tape. So, we see that the buttons have multi-functions depending on the mode you're in, and that makes the functioning very inconsistent and hard to keep track of. So we've learned a lot about error prevention already. So of course we can consult that and say, does the system have ways to prevent and recover from errors? Does this system require a person has to remember a lot of stuff? We want to try to memorize loads on or reduce loads on user memory. Is it customizable and flexible? That's always important. Aesthetics can be part of usability testing. We don't normally think of aesthetics as being part of usability, right? We think that, whether it looks good or not and is appealing to look at, but certainly people might prefer to use technology that is more appealing to look at. So in that sense, pleasant design is certainly an important part of getting people to use and continue to use technology. I've mentioned error recovery already, and then help and documentation, right? So this is a kind of a tricky one because there's a phrase called walk up and use, and that means that we want to have technology that doesn't require people to have to read a whole instruction manual in order to learn how to use it, that they can just walk up and use it, right? But nevertheless, there are sometimes systems that may require that they have some help documentation. And we need to make sure that that kind of documentation is in fact usable in and of itself, that it's searchable and easy to use and easy to find information in the documentation. So usability of documentation is in a way kind of its own area of study. So another way, of course, to test usability is to actually have users use the technology and measure their opinions on it, right? So this can be done in a variety of ways. It can be done in one-on-one user testing, or it could be done in a focus group where you let people sit around a table and just sort of talk about their, feelings about a particular topic. Or you can, if you have a technology that you have already manufactured and you send out and everyone's using it, you can send out surveys to the people who have purchased and ask them for their opinions and ratings of your technology and of your products, right? These are all ways of getting some what we might call user experience measures, right? What are these people's feelings and experiences that they're having when using our product or technology? And then we might try to do things that are a little more objective, right? So these interviews and focus groups and surveys might be just getting subjective impressions, but we might want to try to do some objective measurement here. So we'll do use testing. That is, we'll have somebody actually use the technology, and then we're going to measure their performance, right? So how do I measure performance? Well, if I want to have a person do a task, maybe it's a website, right? And I want them to be able to access information on my website that I've designed. Ideally, I want them to be able to obtain that information fairly quickly. That is in the shortest amount of time possible. And I also want them to be accurate. So I can measure these things. I can measure how long it takes for them to find information. I can measure their accuracy in getting the information that they were supposed to get and maybe didn't get confused and did the wrong thing. I can also ask people to try to report subjectively how difficult they felt the task was. Now that's, again, not necessarily the most objective measurement, but we might wonder if there's certain ways that we might be able to measure the difficulty of a task, not just with a subjective report from a user who's going to say that felt difficult, but maybe there could be some maybe brain imaging or brain recording techniques that we could use to measure someone's workload during a task. And we can also simply just ask people their preference between two different designs, right? So what are some specifics here? So, for example, how do I measure, when people are interacting with a website? This is called clickstream data, right? So they're going to do things like click on links and move the mouse around or something like that. So I can, or if they're typing, right? So I can measure, their rate of typing, how many keystrokes, how many clicks are involved in performing a task, say on a website. And in that regard, then we might assume that fewer clicks is better, right? People are more efficient at interacting with that website. I can look at these intensity measures, as I mentioned, measuring speed, but of course, in some tasks, we might actually be having people perform some more physical action, like interacting with a tool or operating various controls like levers and switches and dials. So I might be interested in the amount of muscle contraction involved in performing these tasks. And of course, measuring time of the task is all relevant here. Here are some more specifics as well. So if I want to measure someone's perceived workload on a task, turns out NASA has invented a well-used rating scale that can be done fairly quickly, right? Just a very quick kind of rating of how much physical and mental work I felt I had to do when I just performed the task that you had me do. And so the TLX is a good way to quickly report my perceived workload. The SUS stands for Software Usability Scale or System Usability Scale. And this is just a simple scale that is fairly well validated and is commonly used and can simply be used to grade a technology. So I think it's scored like out of 100 points. And so you can actually treat it like anything scoring 90 or above, like gets an A, and therefore it has a good usability rating. And if someone has a score in the 80s and it gets a B, that's not bad, right? And so on and so forth, right? Then there might be certain physiological measurements that we can use as well. So if people are using a technology that is difficult, we might find that the difficulty in using that technology causes stress, and stress is associated with physiological arousal. So we might be able to detect their stress with a galvanic skin response. That's one way to do it. So this is a measure of the electrical conductivity of the skin. There are sensors that measure this. It also maybe shows up in your pupils, right? So the pupils dilate. And so we're using an eye tracker that records pupils. We measure the pupil diameter, and that's called pupillometry. HRV is heart rate variability. So if we use an EKG, we can measure their heart rate. Heart rate goes up when we're stressed, but obviously there's also changes not just to the heart rate, but to the timing of the intervals between the heartbeats. And that's what heart rate variability is. There's something called the RR interval. So the heartbeat is actually not just a single beat, but there's these peaks on the waveform known as the QRST peaks. And by measuring the interval between the R peaks of the waveform, we can measure RR intervals and how that varies over time. And that's your heart rate variability. And we see that variations in that can reflect variations in the balance between the sympathetic and parasympathetic nervous systems, and that could tell us something about a person's arousal state. Also, blood pressure certainly also correlates a little bit directly with arousal levels. In addition to subjective measures of workload, maybe some of those HRV and blood pressure, heart rate stuff can also measure a person's subjective workload as well. But we can get into the brain here as well. So there can be certain signals from EEG recordings that will help us find increases in workload. I believe that's the P300 signal, but don't quote me on that. EEG isn't really my thing. And also FNIRS. So FNIRS stands for Functional Near Infrared Spectroscopy. And this works a little bit like fMRI. Instead of using magnetic fields, it uses near infrared light to record blood flow and detect variations in blood flow in the brain. And the idea is that when certain parts of the brain, but especially maybe the prefrontal cortex, are being heavily used, we're going to see a transient increase in blood flow to the prefrontal cortex. And that's associated with, working memory and attention and a lot of those executive functions that are an important part of concentration and high workload. So seeing that transient increase in activity in the prefrontal cortex through FNIRS could perhaps, reveal some degree of increased workload. Some other things is that if people become fatigued, right, when you have to use this technology, does it make you tired? Well, a lot of those cardio measures, again, HRV and blood pressure and heart rate could indicate fatigue. FNIRS can also be used to indicate fatigue. So what can sometimes occur, this is a theoretical question at this point still, that sometimes an increase in activity in certain brain regions is labeled as compensatory activity, meaning that as we perform a task for a long period of time, we begin to get fatigued and our performance declines. So what we try to do is we try to compensate for that by increasing our cognitive effort. And that increase in cognitive effort is resulting in this compensatory pattern of activity in the brain that could be potentially detected by FNIRS. All right, well, I think that covers a good chunk of all that we need for our research methods at this point.